In section 6.4, we are analyzing the work done by varying forces. Our objectives here are to recognize when forces are changing and use appropriate mathematics to account for the work done by these changing forces. We're going to be using integrals to solve work problems, and we will also be working on correctly applying Hooke's law and work concepts to springs. Now let's consider a particle that's being displaced along the x-axis under the action of a force which varies with the particle's position. What we mean by this is there's some object that is being pushed or pulled such that the force pushing it is actually changing as the position of the particle changes. Now we have not dealt with this yet, since our work equation was work equaling the force multiplied by the displacement of the object and maybe some angle to that force, if the force was being exerted at an angle to the displacement. But what we're seeing here is that in this equation, this force was a set amount of force. It was a constant force. And what we're looking at here is what happens if the force that's pushing on this object is actually changing. It's getting stronger and stronger, or maybe weaker and weaker. There are lots of things in real life that exert varying forces. Springs, people, bowstrings, an expanding or compressed gas. There are lots of examples of things that will exert forces that actually change with position. So let's say that these graphs down here are an example or a graph of this varying force. Notice that the force started out weaker and it grew in strength and got stronger as the particle was moving along. The question is, what about this graph is now actually representing the amount of work done? Well, remember, if the graph was a constant force, where this is our f-axis and this is our delta x-axis, if force was constant, we would have said just take that force and multiply it by the displacement of the object. Basically, we would have taken this value and multiplied it by this one here, or really just a length times a width of this rectangle that we're seeing here. Now, since the work in this case would be represented by the area of this rectangle, that is always going to be true of any graph of force versus displacement. It is, in fact, the area underneath this graph that is representing the amount of work that would be done by this varying force. So the question now becomes, well, how do we find that area? If force is constant, it's just taking the length times the width, finding the area of a rectangle, which is really simple. But now we have something that is actually changing. We can still find the area of rectangles, but this would now be an approximation. So we could approximate the area underneath this graph with very small rectangles, assuming that we had small amounts of constant force at this particular value for some little delta x that we're looking at. So this amount of force times that delta x would give you the area of one of these rectangles. We could then add up a whole bunch of these rectangles with constant forces multiplied by these little delta x's for displacements that the object was going through. Now, as we approximate the amount of work done, we would have to add up all of those little rectangles. So essentially, the work would be about equal to the summation of those f values times the little delta x distances, or those rectangles that we were working with. Now, in reality, this is just an approximation. If you want to get the exact area under that curve, we could take these little delta x's and have them become infinitely small, because as the rectangles get smaller and smaller, your approximation is getting better and better. A thinner set of rectangles would be a better approximation to the area under the curve. Now, as these rectangles become infinitely thin, essentially what we are getting is an integral. So work can be thought of as an exact value of that work being the integral from some initial x value to the final of the force with respect to the x-axis. If more than one force is going to act on the system and the system can be modeled as a particle, the total work done would just be the work done by the net force. So now we could write this in as net force, or the sum of all the forces acting on the object, and that would now be the net work, or the total work that was done. If the system could not be modeled as a particle, then the work would have to be found for each individual force, which could then all be added up. Basically, work 1 plus work 2 plus work 3. Work is a scalar quantity, so you can simply add them together the way that we're showing here. This might be a system where you have particles that are moving with respect to each other, where different pieces of the system might move through different displacements because they're experiencing some different forces. Then you could simply add up each individual amount of work. Now let's look at the work specifically done by a spring. We said that springs were one example of work that's done by a varying force. So this is a common system where force is going to change with position. And this is where Hooke's law applies. We've experimented with Hooke's law once before, but here we're going to be working with it much more again. Hooke's law basically says that if an object is located at some position x relative to the equilibrium, where the equilibrium would be considered x equals 0, or an unstretched, uncompressed spring, then the stretched or the compressed spring would exert a force where the force by the spring is equal to a negative kx. K here is a positive constant. It's sometimes called the force constant, spring constant, stiffness constant. Basically, it's a constant given to an individual spring. The stiffer that spring is, the higher the K value would be. And x is the distance displaced from 0, or from the equilibrium position. The negative sign that you see here is there because the spring force is always going to be exerted in the opposite direction as the displacement. So if we were to stretch the spring like we see here, and the displacement is going this way, our spring is going to be exerting a force in the opposite direction. Basically, it's always a restorative force. It's always trying to restore that spring back to the equilibrium position. So if you pull off to the right, the spring is going to pull back to the left and try to restore it. If you compress the spring and push it to the left, the spring is going to try to push back to the right and again restore it to the equilibrium position. We will assume that all springs obey Hooke's law unless it is otherwise stated or asked about in the problem. So imagine that we have a block that is displaced to some negative x max, basically this example here, where you compress the spring some certain distance, and then you release the object to move along a frictionless surface. If that surface is in fact frictionless, the spring will push back towards the equilibrium position. The object would then move through that equilibrium position out to a positive x max, so basically to a position here, and it would continue to oscillate back and forth across this surface as long as you had that frictionless surface, and with no friction it would do so indefinitely. So now we can see that since work is the integral of the force equation, work is the area under that FD graph, or F delta X graph. Because it's the area under the graph, if we had something with a linear change in the force, such as a spring, since a spring follows a Kx kind of equation, or linear equation, we could simply find the area underneath this graph. Area underneath this graph would be a triangle, which would be half of the base. The base is delta x, multiplied by the height. The height is our kx. So 1/2 x times kx would give you a 1/2 kx squared. We could also see this by actually taking the integral of kx dx. Remember, when you integrate, you raise the power on your variable by 1, so the x would now be to the second power, and we would divide by that new power, leaving any constants out front. So in integrating this, we would get a negative kx squared over 2, or 1/2 kx squared. You can see that you could then evaluate this from some xi to xf and get the relationship that we show here. Looking at this equation, it's clear to see that the work would be equal to 0 for any motion that ends where it begins. Also notice that the work would equal 0 when the object moves between symmetric locations, basically an xi equaling a negative xf. This would look like a graph that could look something like this, where the area above the x-axis is equal and opposite to the area below. Again, here these would cancel out and you get 0 work done. So far we've discussed the force and the work done by the spring. But what about a person that would stretch or compress that spring without an acceleration? What we have here in these equations are the amount of work done by the spring. Obviously, if the spring is pulling one way, maybe this is your spring here, the spring is trying to pull back this way, the person might be pulling in the opposite direction as they try to stretch or compress that spring. So the force that the person would exert would be equal and opposite to the force of the spring, and the work would also be equal and opposite. So if you could find the work done by the spring or the force exerted by the spring, the person would be equal and opposite in their force and work done.